So in our last class, we started our description of Fourier series, and we were able to establish that when a signal is periodic, that the Fourier transform gives us some discrete function, okay? So I'll just mention that, I'll write that, Fourier series. So when I say that the Fourier transform of a periodic signal gives us a discrete function known as the Fourier series. Okay. So we already explained this concept because the Fourier transform of a non-periodic signal or a periodic signal is a continuous function, right? We established that point. Now, this is periodic, but the Fourier transform of a periodic, which is the same as non-periodic signal, is a continuous function, right? Say h of omega. Okay. Coming from the transform perspective. And now that we have to take the Fourier transform of a periodic signal, we realize that what we now have is not a continuous function, but rather a discrete function. And since we already know that the periodic signal itself is described in terms of the time period of that signal. And we also know that this time period do have a spread, which we could address or refer to as a linear combination of the smallest value of that time period, which we call the fundamental time period, T0. So meaning we also have T1, T2, T3, T4, for which T sub I taking on values from 1 to say infinity is such that this gives us is the same as alpha T0, or better still, let's be consistent, say I T0, okay? No, let's say alpha T0, okay? So where alpha is an integer value. So we can now move from the fundamental time period to the harmonics, okay? Now, which happen to be the integral multiple of the fundamental time period, okay? Now, we also know that the frequency, the fundamental frequency value is the same as the inverse of the fundamental time period. Okay. Now, we were able to also deduce that based on the spread of this signal, okay, let us just document that and take it up nicely. Okay, so since we've been able to establish that the Fourier transform of a periodic signal is some discrete function, then we can now begin to describe this function. Say phi sub k of t being the same as exponential j k omega naught t being the same as exponential j k. This will be 2 pi over t naught t for all values of k, taking on values from 0, 1, 2, all the way. Okay? And this could be either positive or negative value, positive or negative value. Okay? And at k, k1, or better still at k being the same as 1, we were able to figure out phi 1 of t being the same as epsilon j omega naught, that's k being 1t. And here we see that we have omega naught. And then at k being the same as 2, we're able to see that k sub 2 of t is the same as the Euler or exponential j2 omega naught t. And we see this here, we have 2 omega naught. And should this be the same as 3, by 3 of t will be the same as epsilon j 3 omega naught t, for which we have 3 omega naught. And should k extend to some value n, then phi n of t will be the same as epsilon j n omega naught t, such that we now have, for all of these values, n omega naught. Okay? So you observe that this is the same as the first harmonic, okay? First harmonic, or better still, the fundamental component. And all of these are the integral multiple of this fundamental component, such that this is the second harmonic, and this is the third harmonic, and this is the fourth harmonic. So if, for instance, I have signals flying this way, and say, of all of these signals now forming some kind of irregular shape as a resultant component arising from this, then we are trying to say that should we try to extract, or better say process this signal, we are going to figure out a component of omega naught and the integral multiple of this omega naught up to some n omega naught. And should we be able to estimate this component, we could figure out a way to knock off all of these other components by way of filtration, because they all contain the same information, although distorted. Is that clear?
Yes, sir.
Okay. Now, if that is clear, we now see that the linear combination of the harmonically related components. So if we now take all of these together and put them all together, we now have a sum. Okay? We now have a sum. So that was what led to the signal being described as the sum of the harmonically related components j, k, omega naught t, for which k takes on values from negative infinity to positive infinity. Okay. And this also is the same as this, as sigma k taking on values from negative infinity to positive infinity, a sub k epsilon jk 2 pi t naught t. Okay. Now, you'll observe that this component takes on values from negative infinity to positive infinity. Okay? Should we consider the time points? Now, in practice, we know we actually deal with positive time, not negative time. So let's assume we take positive values of k from positive 0 to positive infinity. So at this point, we have negative 0 to negative infinity. So let's assume we decide to take positive 0 to positive infinity. Then it means that the limits of this summation will change. Okay? Such that we can now describe our signal. Go on, please, Samuel Alozie.
Good afternoon, sir.
Very good afternoon.
You just said something saying in practice you don't deal with negative time, but we deal with positive time, right?
Mm-hmm.
Okay. You just said something about positive 0 and negative 0. In real time or in real practice, is there anything like positive or negative 0? I thought
Okay.
0 was meant to be.
Okay. Your line is your voice is fluctuating. I would love to hear you clearly. You thought what?
I said I thought 0 is a neutral value.
Mm-hmm.
Yeah,
Yeah.
that's why I'm.
Yes, zero is a literal value. But when we consider signals at the point of discontinuity, okay? So let's take this as a plot, okay? So this is a step function, right? And say this is 0, right? Now you realize that this value progresses from negative infinity up to this point. It progresses up to this point. And then at this point, it takes on two values, right? So this is positive infinity. It takes on two values and then progresses. So you now observe that at this point, for instance, this signal is taking on two values at point 0, okay? But technically, we are literally progressing from negative infinity all the way till we get to -1 to some dot to negative 0.01 to negative 0.00000000009, to negative. Now, approximately, just talking in literal terms, approximately to the nearest two decimal point, this is negative 0.00, right? Alozie, isn't it?
Yes, sir. It is.
But we still have some fraction till we get to 0 as it is. And then we move into positive 0.00000 whatsoever till we get to 0.9, then till we get to 1, and
So
then
at that unit step function right there, where it is jumping up, that is when it becomes a positive.
no. Now, at this point, we deal with a particular problem, which I mentioned in our previous lecture, the Gibbs phenomenon, right? So you want to look that up. You don't want to go into that. So at this point of
All
discontinuity, okay? So we have to deal
right,
with a
sir.
whole lot here, but that's fine. But literally speaking, this describes what we have to deal with, but there's an approximation to all of these, okay? Because we now have to deal with
All
some
right, sir.
repo values and all of that. So we are dealing with some approximation. So to clear all doubt, we want to enforce this assumption that we are on true positive scale, right?
All right, sir. Thank you.
Okay, okay, okay. Now let's move on. So now let's change the color of our, okay, perfect. So with this, we can now specify our signal S of t to take on values from k being the same as 0 So I said positive 0, so positive infinity, okay? Such that a sub k is the same as epsilon j k. Let's keep up with our omega naught t. Now, this is a linear combination of the harmonically related components. So we can literally expand this process, okay? Such that when k is the same as a is the same as 0, what are we going to get? If k is the same as 0, so we're going to get a naught, 0 times all of this, so epsilon naught. Now, epsilon naught will give us 1. 1 times this, so our first term becomes a naught. And then we now realize that when k is the same as 1, 2, 3, 4, 5, we are going to have a distribution of this to say plus a1 epsilon j omega naught t plus a2 epsilon j2 omega naught t all the way to an epsilon j2n omega naught t. Okay? So now that we have been able to describe this, we now realize, okay, go ahead, Ekbo, Isaac.
So why is it epsilon j2n? It's not meant to be epsilon j n omega naught t.
So we started expanding this. So when k is 1, this k becomes 1. So we have this expression. When
No, I'm talking about the nth term.
okay, n. Oh, yeah. Thanks for the observation. It's n. That'll be j n omega naught t. Thanks for the observation. Yeah. So, yeah, that's it. So now that we have this, we now realize that this expression could be compressed to this, where the limit for k is now 1 to n or to infinity, right? All the way. So this is infinity and this is infinity, right? So based on what we have, this is not n, it's to infinity. Now, if that is that, so it means that this can be rewritten as a naught plus sigma k taking on values from 1 to infinity, epsilon j, no, ak, so the coefficient first, a sub k, yeah, epsilon j k omega naught t. So where this is the same as this, for which k takes on values from 1 to omega. Now we now observe that this is what we call the Fourier series. Recall, now you will recall that, so I need you to recall that epsilon j k omega naught t is the same as the sum of sinusoids, which is same as cos k omega naught t plus j sine k omega naught t, right? Now, if that is correct, this is S of t, then S of t may be rewritten as a naught plus sigma, k being the same as 1 to infinity, then cos k, that is k omega naught t, a sub k, right? Isn't it? Plus sigma k equal to 1 to infinity, j a sub k sine k omega naught t. Isn't it? Is that clear? Is this clear?
Yes, sir.
Okay,
Yes, sir.
good. Now, if this is clear, we can now expand this process. Let us expand this process. So it means that the Fourier series, which we usually refer to as the trigonometric Fourier series, is the same as A naught plus sigma k, taking on values from 1 to infinity, A sub k cos k omega naught t plus sigma k, taking on values from 1 to infinity, j a sub k sine k omega naught t. Right? So now let's take my real component ak to be the same as a sub n, and then my imaginary component jak to be the same as b sub n. So if we substitute this into this, then we will now say that this is the same as a naught plus sigma k, taking on values from 1 to infinity, a sub n cos n omega naught t, such that k is the same as n, literally. Now plus sigma k. No, now we don't have k, we now have n. Now I have n. And taking on values from 1 to infinity, b sub n sine n omega naught t. Okay. This is the conventional trigonometric Fourier series. Is that okay? Is this clear, please?
No, sir.
Did I hear no or yes?
No.
Okay, tell me what is not clear.
Yeah, I don't really understand why you changed AN to BN.
Okay, so let's put it this way. Assume that a sub k is the same as a sub n, such that j a sub k be the same as b sub n, then k is the same as n. These are coefficients, right? So they're coefficients. So we are literally writing the same thing. So should I invoke b sub n, I'm literally invoking j a sub k, which is the imaginary component, right? And recall your even and odd component of the signal, right? So your complex sinusoids is a typical representation of my even and odd component, isn't it? If you still
Yes, sir.
recall. Yeah. So we are literally putting up the same thing. So I have not changed anything. I've only redefined it. It's more like
So
wearing a different cloth. Okay, go ahead.
yeah, are you trying to say that if you get A sub k, you can impute it into J A sub k and you get your B of n or B sub n?
How do
Do you
you
get me?
how
Like,
do you
since J A sub k is equal to B sub n, I trying to say that if you get the value of A sub k, you can use it to get B sub n.
is the same magnitude. The magnitude of A sub k is the same as A sub k. Mod A sub k is the same as A sub k. So this only says this is my real component of this signal, and this is my imaginary component. Exactly.
It's like you didn't get me.
Now this is what I'm trying to say. The fact that there is a J does not change the magnitude of A sub K.
So like, can get B sub n after getting the value of A sub k.
J A sub K is the same as B sub n. Only that this tells me that should we have A sub K arbitrarily, this tells me that B sub n tells me that this is the imaginary component of the complex sinusoid. Recall, we are dealing with complex sinusoid here. It's actually epsilon j and omega naught t. This is what I'm dealing with. A sub n, which is the same as A sub k, epsilon j, k, omega naught t. Does that make any sense?
Yeah, a little bit.
Okay. Okay, Alozie, tell me.
Yes, sir. When when you resolve the what do you call it? That the Fourier series in like non-canonical form into the first, second, and third harmonics and everything. We shortened or compressed it into A naught plus summation A sub k epsilon j k omega naught t. What's the use of now transforming it into this form that you call the trigonometric Fourier series? Why couldn't you just leave it at what we got before?
You
Was there
mean
any serious?
why transform this to this? Is that what
No,
you're trying to say?
yes, but like this, where you the line
Or
that we got before this,
you mean
where you
S
want
of t being the same as sigma A sub k epsilon j k omega naught t, k equal to 0 to infinity. Why did we move this to this?
yes, yes,
No,
plus
is
A
it?
naught.
Yeah, it's the same thing. It's just that this is in the Euler form, while this is in the sinusoidal form.
All right,
Is that okay?
yes, sir.
So whichever way, we are saying the same thing. We have not changed anything. We have not manipulated any figure. We're only talking in different forms. So this brings us back to your complex functions, right? You recall your complex analysis, your complex numbers, such that a complex number could be represented either in the rectangular form, in the Euler form, in the polar form, but they all mean the same thing, right?
All right, sir. Thank you.
Okay. So now the choice of representation is determined by the complexity of your analysis. Okay? Is
Yes, sir.
that okay? Yeah. And
Yes,
we
sir.
are
Yes, sir.
and in systems analysis and design, we are more comfortable with the eigenfunction, EST, right? Because once we explode this, we are able to deal with the complex, with the sinusoids. Okay? Okay. So can we move on? Sure, we can move on, right? Alozie and Co. Are we good?
Yes, sir.
Okay. Now that we have resolved this, to say, well, everything we're saying here is all the same. Now, the next point is to investigate, or better still, evaluate the values of these coefficients. Okay? So now that we have to deal with these coefficients, we now see that this particular coefficient is related to the sine function, while this is related to the cosine function. Okay? So that becomes the next problem to deal with. Good. So we already know that S of t is the same as A naught plus sigma k taken on values from 1 to infinity, an plus n omega naught t plus sigma k equal to 1 to infinity bn sine n omega naught t. So for us to be able to evaluate A naught, we said one interesting thing to do is to integrate both sides over one time period, because should we have a sinusoidal signal, we know that this sinusoidal signal, or not necessarily sinusoidal, sorry for that, should we have a periodic signal, since the Fourier transform of a periodic signal leads us to a series. Now, should we have a periodic signal, we know that that signal will repeat itself after one fundamental time period. So it will be good practice to evaluate over one time period. So if we integrate this entire expression over one time period, S of t, the t being the same as integral 0 to t naught a naught dt plus integral 0 to t naught sigma k being this taking on values from 1 to infinity an plus n omega naught t plus integral k equal to 1 to infinity bn this dt bn sine omega n omega naught n omega naught t dt. And we already established that the integral of sine and cosine over one time period is the same as 0. So once we integrate this, this is going to reduce to 0, and this is also going to reduce to 0. So we now have these two. Now, once we integrate this, so we're going to get integral 0 to t naught s of t dt will be the same as at 0 to t naught, which will give us a into bracket t naught minus 0, which is equal to a t naught. So since the integral of the signal function, the t is the same as a naught, this is a naught, sorry, a naught, a naught, a naught, t naught, then a naught will be the same as divide both sides by t naught, that'll be 1 over t naught, integral 0 to t naught s of t dt. So once we are given the periodic signal, for instance, for us to be able to evaluate a naught, the first term of the coefficient, then this works for us. Is that clear? Is that clear?
Yes, sir.
So the next thing to do is to evaluate an. So this time we want to multiply both sides by cos n omega naught t, and at the same time integrate over one time period. So we'll multiply by this, both sides by this, and then integrate over one time period. So that will give us S of t cos n omega naught t being the same as A naught cos n omega naught t. Then we integrate 0 to t naught dt. Then we integrate 0 to t naught dt plus integral 0 to t naught sigma k, no, not k anymore. I keep saying k. It's now n. It's now n. And taking on values from 1 to infinity, an cos n omega naught t cos n omega naught t. So cos n omega naught t cos n omega naught t dt will give us cos squared n, right? So I'll just wipe one of these. So that gives us cos squared n omega naught t dt plus integral 0 to t naught sigma n equal to 1 to infinity bn sine n omega naught t cos n omega naught t dt. Okay? Now, once we integrate, now this is a constant, right? Now, once we pull out the constant, should we integrate our cosine? This also reduces to 0. Now, this is a signal, which oftentimes is a complex signal. So when we multiply by cos n omega naught t, then we may be able to get an integrable function. Okay? Then we have cos squared n omega naught t. And once again, once we integrate this, this reduces to 0. Okay? Because here we are going to get negative 1 over 4 sine 2n omega naught t. Then we integrate over the time period. And when t is the same as pi, and we integrate from 0 to pi, then this reduces to 0. Okay? And for this as well, if you want to check, this will give us sine n omega naught t over n omega naught. And once we take our limit from 0 to t, so for t equal to pi, once again, we are reducing this to 0. So that what we now have is this function and this function. So that integral 0 to t naught s of t cos n omega naught t dt will be the same as integral 0 to t naught sigma n equal to 1 to infinity an cos squared n omega naught t dt. Now, you already know the trigonometric process. We have the identities. So you want to walk around the identities, which we showed in our last class. So you know that cos 2n omega naught t is the same as cos squared n omega naught t minus sine squared n omega naught t. So let's change the color for this. And also cos 2n omega naught t will be the same as cos squared n omega naught t minus, now sine squared plus cos squared is the same as 1. So minus, then this will now be 1 minus, right? 1 minus cos squared n omega naught t, right? So once we open this up, so this will give us cos squared n omega naught t minus 1 plus cos squared n omega naught t. So this is going to give us 2 cos squared n omega naught t minus 1. Okay? So, and this is cos 2 n omega naught t. So, it means that 2 cos squared n omega naught t is the same as 1 plus cos 2 n omega naught t. And then this cos squared n omega naught t will be the same as 1/2 times this entire process, 1 plus cos 2n omega naught t, right? So the next thing would be to equate this into this process. So what do we get? Let's change the color. So it means that this will now be the same as integral 0 to t naught. Now the half is a constant, we can bring it out. Then we have 1 plus cos 2n omega naught t dt. Okay. And once we resolve this again, so this is going to give us sine 2n omega naught t over 2n omega naught. So by the time we take our limits over one time period, so once again, this reduces to 0. And for this, once we integrate, it becomes t. So it means that this integral t naught s of t so this will now be the same as a sub n dot 1 over 2 t 0 to t, which will be the same as an dot 1 over 2 dot t naught. That's t naught minus 0, that's t. So this now is the same as an t naught over 2 is the same as integral s of t cos n omega naught t dt, taking on 0 from values from 0 to t naught. So here, an will now be the same as 2 divided by t naught, right? 2 over t naught integral s of t cos n omega naught t dt 0 to t naught. So once again, we've been able to resolve an. And then the next point is to evaluate bn. So for us to evaluate bn, we want to multiply both sides by sine n omega naught t, and then also integrate over one time period. So we perform the same thing. So s of t times sine n omega naught t dt integral 0 to t naught will be the same as a naught sine n omega naught t dt integral 0 to t naught plus integral 0 to t naught an cos n omega naught t sine n omega naught t dt. Okay, let's move this upward. Okay. Then plus integral 0 to t naught sigma, sorry, there's a sigma here, for n taking on values from 1 to infinity, n taking on values from 1 to infinity. Then sine, that will be bn, sine n omega naught t times sine n omega naught t will give us sine squared n omega naught t dt. So once we integrate again, then this is going to give us negative cos n omega naught t over n omega naught t, and want to over the limit of integration 0 to t naught. Once again, this reduces to 0, and then this also reduces to 0, and then we have sine squared n omega naught t. And we already know that sine squared n omega naught t is the same as 1 over 2 into bracket 1 minus cos 2n omega naught t, okay? Using your trigonometric identity. So once we integrate this, then we're going to have, so if we replace this with this, then we're going to have this expression to be the same as integral 0 to t naught sigma bn times n equal to 1 to infinity 1 over 2 1 minus cos 2n omega naught t dt. Okay, go ahead, please, Ugochukwu Emmanuel.
Yes, sir. So I wanted to ask the question. Sir, can you hear me?
Yes, I can. Go
Okay.
ahead.
So like you have been like sine NW naught T over NW naught is equal to 0 cos NW naught T over NW naught is equal to 0 after we integrate. Is there any reason why it's like that?
Okay, that this is equal to 0.
Yes, why cos NW naught T? Yes.
Yeah, I explained that earlier. Now, if you integrate a cosine function or a sine function over one time period, it is the same as 0. You can look up any of the standard mathematics textbook for under your integration of trigonometric functions. Okay?
Thanks, sir.
Okay.
Thanks, sir.
You're welcome. Yeah. Okay. Now, once we integrate this also, so that's going to give us sine 2n omega naught t over 2n omega naught t, and taking limits over one time period, again, this reduces to 0, so that we now have integral. Okay, the integral is gone. So, and this reduces to t once integrated. So we now have bn dot 1 over 2 dot this. Then this over 0 to t naught. So technically, we now have integral s of t sine n omega naught t dt 0 to t naught will now be the same as bn dot 1 over 2 t naught minus 0, that will be t naught. So this is the same as bn t naught over 2. So t, okay, let's make b over 2. So bn will be the same as 2, cross multiply, right? 2 over t naught integral 0 to t naught s of t sine n omega naught t dt. So once again, this gives us the bn coefficient. So going by this, we can now provide a brief summary of what we have done. So we already know that the trigonometric Fourier series is given by s of t being the same as a naught plus sigma n, taking on values from 1 to infinity, an cos n omega naught t plus sigma n equal to 1 to infinity, bn sine n omega naught t, such that a naught is the same as 1 over t naught integral 0 to t naught s of t dt, and then an is the same as 2 over t naught integral 0 to t naught s of t cos n omega naught t dt, and bn is the same as 2 over t naught integral 0 to t naught s of t sine n omega naught t dt. Okay? Now, this is just one form. So I'm going to leave this, my next note, to you as an assignment to prove it. Okay? So this is one. now. So another form is the magnitude phase form. Okay, so this is a trigonometric form. So let us look at the magnitude phase form. There we have S of t is the same as A naught plus sigma n equal to 1 to infinity C sub n cos n omega naught t plus phi n. And then we also have the complex exponential form. Complex exponential form such that S of t is the same sigma n equal to negative infinity to positive infinity S of n epsilon j n omega naught t such that x of n is the same as 1 over t naught integral 0 to t naught S of t epsilon minus j n omega naught t dt. Here, S of n is a complex number. And now we are going to establish the relationship between these coefficients. So should I have my representation in the trigonometric form and I intend to convert to the magnitude phase form, how does the coefficients relate? And what if I tend to convert to the complex exponential form? So now we're going to establish the relationship between the forms of Fourier series, okay? Such that S of n is the same as 1/2 an minus bn. So if I want to evaluate S of n, then if I take 1/2 of an minus bn, then we are there, such that a naught is the same as S of naught, okay? And then S of n will be the same as 1/2 Cn with respect to the magnitude phase form epsilon j alpha n, okay? And then An will be the same as twice the real component of Sn, while Bn is negative twice the imaginary component of Sn. Then Cn with respect to the the trigonometric function is the same as the square root of an squared plus bn squared, so that the angle phi of n is the same as negative tan inverse bn over an. Okay. Now that we have been able to establish the fundamental relationships and the forms of these of Fourier series, then can we say that all periodic signals have Fourier series? So that's one big question that we need to address. Go ahead, please, Ekpo.
So sorry, I don't really understand those exponential form and magnitude phase form.
Yeah, exactly. That's why I say I'm leaving it to you as an assignment. You're going to derive this. Now we've derived this, right? So we've derived the trigonometric Fourier series. So as an assignment, you're going to derive this, or you're going to do a little research over the week and submit this on or before our next class next week. So you're going to derive this and then derive the magnitude phase form and the complex exponential phase form, and then build up the relationship. Okay?
Then where is Cn coming from?
That is what you need to go resolve, is the magnitude of this expression. Okay? And it is a function of an and bn, because this is more like a compressed form of the sinusoids, right? Is that okay? So we are literally saying that what we have here, look, what we have here in the trigonometric form is the same as what we have here, such that this coefficient is a function of the real and imaginary coefficient, coefficient, yeah. Okay? And
Yes, sir.
and that is derived by this. Okay? Well, it's not rocket science, okay? So you're going to derive this, and then you derive this. Then in subsequent lectures, we'll review your derivations. Is that okay?
Yes, sir.
Okay. Now, I just asked the question, can all periodic signals have Fourier series? So this is open to the class for discussion. So can all periodic signals have Fourier series? Okay, so let us interact. Uzo John, can you tell us what you have in mind regarding the question? Okay, Uzo John is not in class.
In class.
Okay, so tell us, can all periodic signals have Fourier series?
Yes, sir.
Okay, why is that? Why is that? Tell us the reason. Okay, so we need to buy some time. So any contribution from anybody in class on this?
So I decided to do a quick search, and apparently it says that not every single periodic signal can be represented in the form of a Fourier series. But you can use it to represent most periodic signals you encounter, but you can't represent all of them. I think maybe what is happening is that you can't integrate every single signal. So because of that, you might not be able to get a Fourier series for every one of them.
Okay, well,
Continuities too. Well, yeah,
beautiful contribution. Well, we don't want to bother ourselves with integration. We have softwares that could do that for us. But the idea is that for a signal to have Fourier series, it must to some extent satisfy some conditions. And those conditions are called the Dirichlet conditions. Okay? So for a periodic signal to have a Fourier series, then these conditions must be satisfied. And the first of these conditions is that the signal S of t must be absolutely integrable, that is, over one fundamental time period. So meaning if we integrate the modulus of that signal over one fundamental time period, it should give us a finite value. Okay, so it means that the signal must be absolutely integrable over the range of time period, or over one fundamental time period. Okay. And then the second point is a measure of the discontinuities. Okay. So it means that the signal must have finite numbers of discontinuities over that range of time period. So if, for instance, we have the signal, then in this case, how many discontinuities do we have here? So this is S of t and this is t. So how many discontinuities can you see?
2.
Is it 2?
3.
So 3.
This is 1, this is 2, and this is 3. So is this finite? Yes. So the signal must have finite number of discontinuities over the range of time period. And this is the range of time period, 0 to t0. So we have 1, 2, 3. Then the signal repeats itself again. Now, the third condition a necessary condition is on the number of maxima and minima. So it should have finite number of maxima and minima over the fundamental time period. So if we have a signal, say this, and this is the time period, so this is the maxima and this is the minima, and that is finite, right? Over this time period. Okay, so it means that the signal, so this is S of t, this is t, so the signal S of t should have finite number of maxima and minima over the range of time period. Is that okay? So now that we've been able to establish some sufficient conditions for a periodic signal to have Fourier series, then the next thing that comes to mind is, why do we want to perform this operation? We want to be able to tell the frequency components of the signal. And then we want to be able to also estimate the energy content of the signal, okay? Whether to amplify or to attenuate or whatsoever way, depending on whatsoever we want. So, depending on the application. So the next thing we now want to talk about is, how do we evaluate the energy content of periodic signals? How do we evaluate the energy content of a periodic signal? And this is pretty simple and straightforward. It brings us to Parseval's theorem. And what does this theorem tell us? It literally tells us that the energy of a signal in the time domain, say 1/1 time period over t naught, recall that it is the mod squared of that signal, the t, this gives us the energy. That the energy of this signal in the time domain is the same as the energy of this signal when transformed to the frequency domain. So for which n is equal to negative infinity to positive infinity mod s of n, let's use the proper notation, s of n mod squared. Okay. So this is what the Parseval's theorem says, that if we are able to tell the energy of the signal in the time domain, that energy content of that signal must be the same, even when the signal may have been transformed to the frequency domain for ease of analysis. And when you look up the lecture notes we uploaded previously, then you'll be able to look up how this was derived. Okay? And then one other interesting thing to now do is to evaluate one of the examples. So let us run through this simple example. So let's assume we have this signal. So this is a signal. This is 0, 2 pi, so 4 pi. So one time period is 0 to 2 pi, t, s of t. It's a continuous time signal. Okay, so let us evaluate the Fourier coefficients of this signal. So you have been given this problem to solve. You want to evaluate the Fourier coefficients. So the A0, AN, and BN. So what's the next thing to do here? So the first thing is to figure out the equation for this signal, okay? So you recall your equation of a straight line, right? And then we want to get the gradient and the intercept, isn't it? And for the gradient, say M, okay, let's just do that here. Say M, that will be x2 minus s1 over t2 minus t1, which will be the same as, now here, we have this amplitude to be 1, right? So s2 minus s1 will be 1 minus 0, 1 minus 0, over t2. I'm sure you must have done this too in your fundamentals of electrical engineering. So this would be t2, 2 pi minus 0, 2 pi minus 0 over 1 time period. So this will give us 1 over 2 pi. Okay? And now we know that the equation of a straight line, this is a straight line, right? This is a straight line. Now the equation of a straight line is given as s of t being the same as the gradient times t plus the intercept. Okay? So we already know the gradient, and here there is no intercept, so which is 0 because it is going through the origin. So c is the same as 0, so that this signal s of t will be the same as 1 over 2 pi t, which is t over 2 pi. Okay? So it means that our signal s of t is the same as t over 2 pi. So we can now work with this, okay? So I'll just play with the first, and then, okay, we still have some time. So recall that A0 is the same as 1 over T0, integral 0 to T0, S of t dt, right? So we plug that in, so that will be 1 over T0, integral 0 to 2 pi, right? Because that's the time period, and T0 is 2 pi, so let's load that in also. 1 over 2 pi, 0 to 2 pi. Then S of t is t over 2 pi dt. Okay. So this now will give us 2 pi comes out 1 over 2 pi. So that's 1 over 2 pi times 1 over 2 pi. That's 1 over 4 pi squared integral 0 to 2 pi t dt. Okay. So this will give us 1 over 4 pi squared t squared 0 to 2 pi. Okay. So and this now t squared over 2, right? That's the integral. So t squared, that's t n minus 1 over n minus 1. So no, for t, no, t squared over 2, yeah. N plus 1, that's t n plus 1 over n plus 1. So that's 1 plus 1, that's t squared over 1 plus 1, 2. Okay. So once this is done, then we can bring that out. That's 2 pi squared, that will be 4 pi squared over 2 minus 0. So we have 1 over 4 pi squared into bracket. 2 pi squared will be 4 pi squared over, that's over 2 minus 0. Yeah. So this strikes this out. So A naught is the same as 1 over 2, right? So we are done with that. So the next thing is to figure out the next coefficient. Let's rule a line here. Then we resolve an, a sub n, the same as 2 over t naught integral 0 to t naught s of t cos n omega naught t dt. Now we have omega naught in this case, but we know that omega naught is the same as 2 pi over t naught. And we know t naught is 2 pi, so omega naught will be 2 pi over 2 pi, which is the same as 1, right? Rad per second. So it means that an is the same as 2 over 2 pi, 0 to 2 pi, s of t, that's t over 2 pi, right? Then cos n, omega naught is 1, so nt dt. Okay? Is that clear? So these two can strike these two out, pi times pi. So this will now be 1 over 2 pi squared, 2 pi squared, 2 times pi, integral 0 to 2 pi cos nt dt. Sorry, this t cos nt dt. Okay? And now that we have t cos nt dt, we can actually use integration by part, which is integral u v dt, which is the same as u integral v dt minus integral du dt integral v dt dt. So once we do this, then we should be able to address this, where this is u, and then this is v dt, and then we are able to address this expression. Okay? Does that make sense, please?
Yes, sir.
Okay. So it means that u is the same as t. Then we have the integral of v dt, so integrate cos nt, so that will be times sine nt over n minus integral du dt. Okay, so if this is u, so what is du? that will be 1, right? Good. That's 1 times, then integrate that. So that will be sine nt over n dt. Okay. And so once we integrate this expression, so what do we get? So we are going to integrate this now. So it means this will be negative cos, right? Once we integrate this, negative cos, then over n. So that will be n times n. So this becomes n squared. So we are now going to have integral. That's what we are dealing with. Integral t cos n t dt will now be t sine n t over n, which is this, plus, because this is now going to give us minus cos nt over n, and that will be n times n. So that minus times minus will give us plus, then cos nt over n squared. Is that clear? So we are now going to plug this into this expression, you know, so we now have so we now have a sub n to be the same as 1 over 2 pi squared t sine nt over n plus cos nt over n squared 0 to 2 pi. Okay. So once we plug in 2 pi into this, sine 2 pi will reduce to 0. Then cos 2 pi will be 1. So what we are saying is that an will now be the same as 1 over 2 pi squared into bracket 2 pi. If 2 pi is here, 2 pi sine n 2 pi over n plus cos n 2 pi over n squared minus, when this is 0, this will be 0 times sine 0, that's n 0 over n plus cos n 0 over n squared, right? Everything in square bracket, right? So this will give us 0 sine 2 pi, which is sine 360. Now this is going to give us 1. This is going to give us 0, and this is going to give us 1, right? So this will now give us an equal to 1 over 2 pi squared into bracket 1 over n squared, 1 over n squared minus 1 over n squared. Okay, minus times plus. Okay, and this minus this will give us 0. So it means an is the same as 0. Okay, and now we'll now perform the same operation to evaluate bn. Okay. So we already know that bn is the same as 2 over t naught integral s of t sine n omega naught t dt. Okay. And we know s of t is t over 2 pi. So this will give us 2 over 2 pi integral 0 to t naught, 0 to t naught, t over 2 pi sine n omega naught t dt. And then what we get from this, so this we truncate this. So we now have 1 over 2 pi squared integral 0 to t naught t sine n omega naught t dt. Now we already know that omega naught is the same as 1, right? Because omega naught is the same as 2 pi over t naught. And t naught is 2 pi over 2 pi, that's equal to 1 radians per second, right? So Bn is the same as 1 over 2 pi squared integral 0 to t naught t sine n t dt. So once again, we can resolve this using integration by path. And then we now have t integral sine nt dt minus integral dt integral sine nt dt. Okay. And this is going to give us negative t cos nt over n minus integral dt is 1 times, and this is going to give us minus cos nt over n dt. So that integral t sine t dt will now be the same as negative t over t, that's t cos nt over n minus times minus plus cos. Okay, let's bring out this. Let's bring out the 1 over n. 1 over n integral cos nt dt. Okay. So once again, this will give us negative t cos nt over n plus 1 over n sine n. Once we integrate this, nt over n. Okay. Then this will be the same as negative t cos nt over n plus sine nt over n times n squared. So we now see that Bn is the same as 1 over 2 pi squared, or 2 pi squared into bracket minus t cos nt over n plus sine nt over n squared 0 to 2 pi. So just the same way, so if we substitute 2 pi into this and into this, then cos n 2 pi will be the same as 1, while sine n 2 pi will be the same as 0. So we are going to have 1 over 2 pi squared into bracket minus 1 plus 0. Now, once we substitute 0 into this, so minus 0 times whatsoever, then that reduces to 0. Then sine 0 will also reduce to 0. So it's going to be minus into bracket 0 plus 0, right? So this will now give us minus, that's 0 over n, right? Minus 1 over n, right? Then Tn is 2 pi, yeah? So let's document this correctly, please. Because it's 2 pi, so that will be minus 2 pi times cos 2 pi n, that reduces to 1 times 1 over n, yeah? So that'll be, yeah, so we're in order now. So this will be the same as minus 2 pi over n. So times this. So minus times minus, so 2 pi, we truncate 2 and we truncate 1 of this. So we have pi n to be minus 1 over pi n. So Bn is equal to minus 1 over pi n. Okay. So with this, we know that An is equal to 0. And then we know that A naught is equal to 1/2. So we can now substitute this into the Fourier series equation. That is, we know that S of t is the same as A naught plus sigma n equal to 1 to infinity An cos n omega naught t plus sigma n equal to 1 to infinity Bn sine n omega naught t. So we know A naught is the same as 1 over 2. An is the same as 0. And then Bn is the same as negative 1 over pi n. So once we substitute this, so S of t will be the same as 1 over 2 plus, now An is 0. So this expression reduces to 0 plus 0, then plus Bn. So this is going to be sigma n equal to 1 to infinity into bracket. Bn is minus 1 over pi n, right? Sine n omega naught t, right? So minus times plus, so that will give us 1/2 minus sigma n equal to 1 to infinity 1 over pi n sine n omega naught t. But omega naught is the same as pi. It's the same as omega naught is the same as 2 pi over t naught equal to 2 pi over 2 pi. It's equal to 1 radians per second. So that S of t will now be the same as 1 over 2 minus sigma n over 1 to infinity 1 over pi n sine n t. So going by this, having established all of these, we can as well derive the coefficients for the complex exponential and the magnitude phase form and represent same in that form. Is that okay? Is this clear, please?
Yes, sir.
Okay, so before we move on, any question for now? Because this is where we'll call it a day for today. And then we'll move into applications in our next lecture. Okay, where we'll begin to play with real-world applications. Okay, so how does the transforms and the likes apply? So before I move into other details, any question?
Sir, regarding the last slide, you were having minus sign. I don't know if you can refer to the slide. So I was wondering what like maybe you just assume n to be equals to 1, or like was it stated regarding the last slide?
Is it y deriving Bn? I didn't make any assumptions. Was it?
Yes, sir. Why deriving I mean from the last slide.
Okay, if I have to move to the last slide, then I'll have to just move. Okay, don't worry. I'll do that right quick.
You were able to eliminate the minus t cos nt.
This?
Yes, sir. Like meanwhile the value of n was not stated. Like if we had to put 2 pi, it would just replace t.
No, we have 2 pi. So the magnitude of that, we are taking the nth magnitude. So if we say 2 pi times 1 is 2 pi, 2 pi times 2 is 4 pi.
Oh,
So cos 4 pi is still 1. right?
Oh, okay, sir.
You get,
Thank you, sir.
yeah. So on the nth order, as we're increasing that magnitude, we still get that one.
Oh, thank you, sir.
Y for sine, we get zero, right? Okay.
Thank you, sir.
You are welcome. Okay. Now, if that's the only, okay, we still have another question. Go ahead, Kelvin.
All right, sir. Good afternoon, sir.
Very
So,
good.
sir, as against to next class, is there anything we need to prepare?
Yes, your MATLAB, your Python, anything you know you'll be able to use to simulate or model signals and systems, yeah, would be appreciated.
All right, sir.
Okay, so we just want to play with a few applications. Since you all cut across different disciplines, signals and from systems engineering, biomedical engineering, electrical and electronics engineering, computer engineering, all taking this course. Then I want to look up one or two real-world application or applications, then see how the signals and systems theory apply. And then you could take things up from there to begin to resolve any problem of any challenge of your interest within the domain. I'm sure that will be fine, right?
Yes, sir.
Okay. So if that's what it is, I think this is a good place to stop. And hope to see you next week. Bye for now. So see you next week, God willing. Okay?
Thank you, sir.
Yeah, bye for now.
Thank you, sir.
You are welcome.